Hello everyone. In today's lecture, we will discuss about logic gates. So the main goal to study about logic gate is to understand how a digital system or a digital computer can work at the lowest level and the possibility and limitations of the digital computer with respect to logic gates. All digital computers for the past 50 years have been constructed using the same type of components. These components are called logic gates. So basically we have 7 types of logic gates: AND gate, OR gate, NOT gate, NAND, NOR, exclusive OR and exclusive NOR. So using these logic gates as components, all the digital computers for the past 50 years have been constructed. So these logic gates have been implemented in many different ways. Nowadays, logic gates are most commonly implemented using electronic VLSI transistor logic. All the basic gates have ability to accept either one or two input signals depending upon the type of the gate and generate one output signal. Here we will see a single input gate as well as two input gate. The single input gate accepts one input and produces one output. The two input gate accepts two inputs and produces one output. When we see about the characteristics of input and output signals, the input and output signals are binary. So binary means always in one of the two possible states. So typically it is treated as either on state or off state. Means electrically 1 or 0, that is logically true or false. We can also represent the treat the state as high or low. So there is a delay between when a change happens at a logic gate's input and when the output changes, called switching time. The true or false view is most useful for thinking about the meaning of the basic logic gates. So as we already seen, there are 4 basic logic gates: AND, OR, XOR and NOT. Each of these gates may be drawn in either a generic form or an electrical engineering form. So more commonly that is used in textbook. So now let's see about the AND gate. So first we'll see the block representation of an AND gate. So here you can see the AND gate is represented in a block in a rectangular shape, and it has two input signal as a minimum number of input. It can be extended output to n value, and it has a single output signal. So here the input signals are marked as I1 and I2, capital I1 and capital I2, and the output signal is represented as capital Q. And the classic electrical engineering AND gate symbol is given. So this is how the AND gate is represented in the all the circuit designs and textbooks. The output signal from an AND gate is true, which means on or 1, if and only if both input signals are true. That means if both the input signals are on or 1. The output signal from an AND gate is false, that is off or 0 when otherwise, meaning that when both the input signals are not true, the output is equal to 0. So this is a general logic behind AND gate. Based on this logic only, the AND gate truth table will be formed. Next we will discuss about the OR gate. So similar to AND gate, here we can see a block level rectangular representation of an OR gate and a classic electrical engineering OR gate symbol, the right hand side. So with respect to the OR gate, as like AND gate, here also it accepts minimum 2 input signals, and the inputs can be extended up to maximum of n value. The input signals are represented as capital I1, capital I2, and the output signal is capital Q. Next we will discuss about the logic behind OR gate. The output signal from an OR gate is true, that is on or 1, if either or both input signals are true or on or 1. So meaning that when we compare the input signals I1 and I2, When any one of the input is equal to 1, the output is equal to 1. The output signal from an OR gate is false, that is off or 0, if and only if both input signals are false, that is off or 0. So this is general logic behind OR gate. Next we will see about the XOR gate. So here we can see the block level representation in the left hand side and the classical electrical engineering XOR gate symbol in the right hand side. Similar to AND and OR gates, XOR gate also accepts minimum 2 input signals, maximum of n input signal. The input signals here represented as capital I1, capital I2. The output signal is represented as capital Q. Next we will discuss about the logic behind this XOR gate. The output from an XOR gate or exclusive OR gate is true, meaning that ON or logic 1, if and only if the input signals are different. Or else we can say it as when the input signals are not equal or not same, the output is equal to 1. The output from an XOR is false if the input signals are either both true or both false, meaning that when both the input signals are equal or 0 or 1, the output is equal to 0. So the next most important gate is NOT gate. You can see the block level as well as symbol row representation. Block level representation is given on the left hand side. It has a single input and single output. So that is the main difference between a NOT gate and another gate. It accepts only one input. And the classical gate symbol representation which is used in electrical engineering circuits is given as in the right hand side. Next we will discuss about the logic. The output signal from a NOT gate is true, meaning that ON or 1 if and only if the input signal is false. The output signal from a NOT gate is false, meaning that off or 0 if and only if the input signal is true. So very simple, the output is just inversion of the input. Next we will discuss some other gates. Note that we have seen a classic symbol representation for all the gates. So now let us see about the NAND gate. To construct the NAND gate, we will take the AND gate and we will insert a bubble at the output. So bubble means it is a NOT activity. Either we can represent the NAND gate as like in the left hand side representation or in the right hand side representation. So most commonly the NAND gate is represented as like in left hand side representation. So the similar functional symbol representation is also given at the bottom. The combination of AND block and NOT block and the combination of AND block and NOT block as a separate and a combined version. In both the cases, AND accepts 2 input and NOT accepts a single input. The output of the AND, that is single input, is given as the the output of the AND, that is the single output, given as the input to the NOT gate. So like this we can construct the NAND gate by combining the AND gate with the NOT gate. So that is why the topic is mentioned as NAND by using NOT combined with other gates. Here the other gate is AND gate. So similar to NAND gate, we can also construct NOR gate. How can we construct NOR gate? We can construct the NOR gate by combining the OR gate with the NOT gate. So this slide shows the analysis of the circuit with feedback. This we will discuss in the later part. So I hope you understand the concept of logic gates, that is basic gates and or not, and we have seen the XOR gate. So based on these 4 gates, we can construct the remaining 3 gates, that is NAND, NOR and XNOR. So out of these 7, NAND, NOR will be called as universal gates. We will discuss in detail about the universal gates and the analysis of these logic gates